Hey guys, good morning. Aircraft structures 2, unit number 2, shear flow in open section. We are going to see the problem number 3 and problem number 4 in today's lecture. So, plot the shear flow distribution. We have to draw the shear flow distribution for a vertical load. We have the vertical load del Sy or we called as V, right, of 1200 Newton through shear center. That means this 1200 Newton is acting in shear center. Shear center is a point where if the load is acting, then the structure get deflection without twisting. That means deformation without twisting, bending without twisting. So no twisting will occur, only deform will occur, bend will occur, right, for the given section, right. So they are given a channel section and they said as it is symmetric about only x-axis. If you cut within this element and x-axis, this equal part will get. That means it is symmetric about x-axis, right. So and the thickness of the entire channel section is 2 mm and the this is a flange, this is web. This is top flange, this is bottom flange, right. So we have the web length of 40 centimeter and flange length of 30 centimeter, right. The given data are, the given is Sy, that is vertical load of 1200 Newton, and Sx they are not given, that is we have 0, right. So we need to form the elementary table. Guys, these are last two problem. We seen the boom problem. This is not boom problem. This is unidealized structure, not idealized structure. We have the original structure. We are not making this as idealized one. We are taking the length and width and thickness, everything, right. So we need to form the element table. So in this case, for this element table value, we usually used to find the element table summation of Ax, summation of Ay, summation of Ax square, summation of Axy, Icx, Icy will find out. So in this problem, the element table value summation of Ax, summation of Ay square and summation of Icx. Guys, here we used to find the Icx. This is not boom problem. If the boom problem means you no need to find summation of Icx, Icy. This is normal problem. So we need to find the summation of Icx. Only can be found because the given section is symmetric about x-axis. So the y bar will be 0, Ixy will be 0 and Iyy is not required for this problem. So we solved n number of problems. From these things you have to understand that when the section is symmetric about any axis means, for example, if the symmetric about x-axis mean, then definitely you will get y bar equal to 0, Ixy equal to 0, and for the problem solving you no need to calculate Iyy is not required for this problem because no horizontal force. If the problem they given me horizontal force means, that means if the problem is about symmetric about y-axis mean, then no need to find of x bar. Again similarly you no need to find of Ixy and no need to find of Ixy if the load is in horizontal, right. So for this problem we need to find the elementary table without those elements. So only we have 3 elements. So I splitted this top flange as 1 element, this web as 2nd element, bottom flange is 3rd element. So I have 3 elements. The area I will calculate for the element 1. Length will be 30 into 2, say 30 meters, 30 centimeters, 2 meter will get. So we will calculate everything in the meter square, right, centimeter square. So we have 6. Area of the first element will be 6, area of the second element will be 8, third element will be 6. So if you add this value you get 20. So length x of this each element from this axis, and we will have the reference of, this is our reference. So x and y will get, for element 1 will get the 15 centimeter x location. And why? Because for if you take the element number 1, I already explained those things. Take only the element 1. You need to find out this center. So if this is your axis means, you need to find out what is the x location and what is the y location. So x is totally this 30. So if you calculate 50%, half of this means 15, and this length will be 20. That is why we are getting 15, 20 for the first element. Second element, it is there in the axis itself. So no, it is if you draw the second element here, second element here, if you draw this x comma y here, x comma y, then center of this point will be x comma y will be 0, 0. For third element, similarly for the third element, it is x equals 15, y will be minus 20. This is symmetric axis, it is below 20, so minus 20. Now you need to calculate only ay square for the a into y equal to 2400, and you will get this centimeter square, and this will be getting minus plus 2400. Why? Because ay square, if you get the square term, then you will get this square value. Though y is 0, then it will get terms will be 0. Ax equal to this value. Again ax will 0 for this, ax will 90, you will get a summation value. ICX for the each element, ICX you need to find, ICY you no need to find, you will not use in the problem. So I'll solve the ICX for the both three sections, all the three sections. So this is a flange and web. Two flange we have, one web we have. So this for both case flange and web, ICX will be B dq by 12. Breadth will be for top flange is 30, this is 30. D will be thickness equal to 0.2, so centimeter. So we will get divided by 12. So B dq by 12 will be for both flange. Top flange are the same value, bottom flange will be the same value, 0.02. And web will be again B dq by, already I told, if this is web, this is always B, this will be D, right? Similarly, if we are solving for the web means, this is always B, vertical will be the D. So B will be 0.2 into D will be 30 cube by 12. So you are getting B D cube by 12. So this is 30. So we have 40. This is 40 cube. So we are getting this value, right? So next we need to find the x bar and y bar. While solving the problem, we will use this whether we are getting going in the right way or not. So we used to solve the x bar equal to summation of a by summation of x by a. You are getting 9 centimeter. Y bar absolutely 0. If you solve, you get the same value. So next we need to determine the moment of inertia Ixx, Iyy, Ixy. So in this problem, we need to find Iyy and Ixy. So only we need the Ixy. This is the not boom problem. That's why summation of ICX we need to find. Summation of Ay square minus summation of Ay bar square. This is a formula. Y bar 0, then this term will equal 0. Summation of ICX we find out at. Summation of Ay square we find out at. So if we get Ixx value, we got this value Ixx. Right? Second, we need to find the determination of the x bar and y bar. So here we have for the vertical load, they are given directly vertical load. S of y equal to 1200 Newton and sy equal to 0. This is Iyy 0. Because of this Iyy 0, x bar is equal to sy. So sy bar equal to sy bar. If you substitute the entire equation, you will get the same value around. Why? Because Iyy Ixy is 0 means, so entire remaining terms will be get 0 in the formula. So we identify the x bar, xy bar, we find out that. Then next we need to find out the shear flow. We know the general shear flow formula for the normal structure, not boom structure. This is the normal structure. This is the boom structure. This is for normal structure formula we know, right? Minus will come for this shear flow. S of S bar, Sx bar divided by Iyy integral of xt ds minus Sy Ixx integral of Yt ds. These terms, two terms will come. Already we derived this. So here we have the Sy Xx bar equal to 0. So this term will cut, entire term will cut 0. Only we have this term Sy bar divided by Ixx integral of Yt ds. This is the only term we'll have. So here if the ready made we have to, if you change this as y as then once the given vertical load, directly you can write as minus v by integral of Yt ds. Mostly in GATE exam, people will ask the problem. Same problem will come in GATE exam with different value. So you no need to solve all this everything. Just you directly they will ask in particular location what is the shear flow. So that time we will directly use the v by minus v by I integral of y dt ds. If you know this formula, you can directly solve in the GATE exam. So if the formula q is equal to minus v by I integral of y t ds. So this is minus v value we know, vertical load, Ix's value we know, into this t is thickness is common, so I taken this from the out. So t equals 0.2. Integral of y. This is the function of that our problem. So ds equal to qs equal to minus half. You solve this value 0.0419. Integral of y ds. So guys, remember, kindly note down that in integral y ds, you need to understand the mathematics. So for this problem, shear flow will start from the let us think shear flow due to this vertical load. The shear flow will goes maybe in top to bottom or bottom to top. Right? So we have whether due to this vertical load, shear flow. I already told shear flow is a shear stress into thickness. So due to this load, flow will be bottom to top or top to bottom. Due to the applied load, the shear flow will be vary. Right? So let us find out those shear flow values and diagram. So let us take the flange. Let us go with the bottom flange. Why? Because that we will taking it separately, then we will apply for the everything. This is symmetric. So no need to find the entire value for the entire section. If you find out the shear flow for the half of this section, then the symmetric of the same value will become for the top section. So if you find top or bottom, and you take one of the section and solve this value and put the same mirror value for this bottom flange. Why? Because it is symmetric about the x-axis. So I am drawing only the bottom flange here with x-axis here, y-axis is here. We have the distance 20 and 30 centimeter, thickness of 0.2 centimeter. For this we need to write this y, x and ds formula. Y will be, what is this entire bottom flange? Common will be the entire location, this entire flange. Y will be common at any location. Y will be 20, that is minus 20. Below x means minus 20 at any location. So that's why I am directly putting y equal to minus 20. And for understanding, so if you find out y, what will be the x means? X will be, so S is shear, right? At this point will be, you have each location, you have different shear value maybe, right? So that's why I am saying this is entirely we have 30 centimeter. So 30 will be added at each shear center location. S1, S2, S3, S4, S5, S6, S7, S5, S8. So you have n number of S will get. That's why X will be varying with each location. That's why I am putting as x1 plus 30. This is the function value, mathematically function. So here we are calculating dx. If you solve this, you will get dx, the rate of change of ds means ds will come, this constant will go out. So for q equal to minus of this value integral of, we need to put the y value, that is minus 20 ds. So if you solve this, so what you will get, this constant, only integral ds will be there, this will come out, and plus 0.838, integral of ds will come. This integral is applicable for only this bottom flange. So you need to apply, this is, we will start from this left end, right end. So we have to solve saying that S will have, this is 0 to 30 centimeter, we are starting from this to this. So at 0 what is the value? At 1, 2, 3, 4, 5, 6, 7, 8 up to 30 what is the value? I will starting with 0 and ending with 30. Right? First I will put the S value equal to 0, then I will getting QS at this point will be, that is Q equal to US equal to this entire term will get S, right? 0.838 into S. We need to substitute at each location, that is why S1 to S2 I put. So first location I will solve from here. So S1 equal to 0, second location at 30 distance I will find. So first 0 and 30. First 0 I put, I got shear flow will be 0 at this location. And when put I 30, when I put 30 I will getting 25.14 Newton per centimeter at this point. So for the bottom flange, at this point shear flow is 0. But at this 30 distance it will get 25.14. 20 this value, it has new value, high value, right? Here it is 0. So bottom flange we calculated the Q S1 to S2, this location to this location, it is 0 to, it is gradually increasing and up to 25.14 it is getting. Next web we have to solve. So similarly have the x-axis, y-axis, web is this same in this axis. So we have same q equal to minus 0.0419 integral of y ds, plus always you need to add this value, last term or the additional terms of last value we find out from the shear flow that you have to add. So for this case we need to calculate x and y. For this case x is 0 for any location, of this web you will get x will be 0. But y will be varying in each point. This point is y. Y means this is y 19. Why? Because we have 20. So 0, 1, 2, 3, 4, 5, 6, 7, up to 20 it will vary. So this is minus 20. Here we are getting the minus value. That's why we are saying in terms of shear flow value, y will be is equal to, in this entire length I am splitting into 2. This I am saying as 20, not taking 40 value. Only 20. And saying that each location s will be varying with effect of minus 20. If you reduce this value, then this term y will be varying. Right? So y will be function of s2 minus 20. I am getting this value. So I am substituting y will be x2 minus 20 integral of ds. So I am integrating this s2 square root by 2 minus of 20 s2 plus this is old value I have. Right? Now again I need to find out the what will be the s value for the vertical flange. So I used to calculate from here to here only, not the entire length. Here to here only I am going to calculate. So S2 will be 0, here 0, and this will be the 20. Why? Because we are going in 0 this way, 0 to L distance, 0 to 20 distance. It is in moving upwards. So that's why I am putting 0 to 20 value, positive value. Q, then you substitute here, substitute 0, then you will getting the same value of 25.11 will be the, at this point you will get the same value, right? Then you apply the 20 here, 20 here, you will getting 32.43 for the, at this location. We are calculating here to here only. So, it is a symmetric section for the shear flow. For the section will be, so initially this is a shear flow diagram. So, once you get the half of the value, remaining will be, you do the mirror for the symmetric section. At the 0 position, I get the 0 value of shear flow Q value. Up to Q1, we are getting, this is 25.14. Up to here, I am drawing this taper line. Right? Taper line, it is gradually increasing. Right? And if you draw this, it will be linearly going. This is linearly, it will take the variation of shear flow. And here, I got the same value what I got here, 25.14. Right? But here I am getting 32.43, this value we got. So this is parabolically, it will vary. So I got up to this value I got. I mirror this value to here. I have drawn this value. Why? Because it is symmetric about x-axis. So same value will come. So we drawn from here. That's why I am drawing for bottom flange. This arrow I am indicating. This arrow for shear flow is moving this direction. Again I am calculated in this direction and it is going top way. That is what it is. Open section, and we are calculating the shear flow diagram. This is a diagram very much important. Once always used to draw, they ask to draw the shear flow diagram only, right? So then we need to calculate shear center location. If we want to get this structure, this is a 3-dimensional structure, right? This is we are cutting and getting the value. This is a 3-dimensional structure. This may be a wing structure or fuselage or any other structural components in aircraft, right? This is a 3-dimension we have. This is an open section. So if you want to find at which location if I apply this load, means it will get only bending. Structure will get only bending without twisting. That point we have to calculate. That is shear center we have to calculate. So that's why we are taking shear center location or shear center distance. So this is 120,200 acting in somewhere. I am saying we don't know what is the exact value of location of Ex. So we need to calculate taking a moment about this point. This point means C point, ABC. C point will take moment about the C point. So we have force in the distance. 1200 into Ex will be the clockwise distance plus. So this diagram will not come. This diagram will not come. Why? Because it is force is in this axis. Taking moment of this point, distance will not come. So only this triangle we have. So what is the force in the distance we have? We need the force. To calculating that force we need to calculate. First we need to calculate the area of this. Area of B into H. That we need to calculate into the entire length will be the force. So area into distance is 30. This is the force. Right? This is the force. This is area. This is the length. of the length of the section into distance will be, this is force, this is perpendicular distance, this is perpendicular distance we have up to 40, this is perpendicular distance. So force into distance we need to calculate, force into distance, force will be classified into area into length, area will be of B and test of the shear flow, into distance will be 30, D will be 40. So if you solve this, we are getting E equal to both, everything are in same in clockwise, that's why I am putting in one in equal to 0 in same direction. So E will be 12.57 centimeter for this case. So we have, if you do this and you will get minus this, if you get minus here, so we get minus 12.55 centimeter. That is, in this axis you have minus, right? This is 0,0 means positive value, minus from this you have up to minus 12.57 centimeter. If you apply this load, means this structure will get only bending, twisting will not occur. If you want to mount an engine or anything, that is the location we have. So if you go for an aerofoil, if you go for an aerofoil or a wing or three-dimensional case, we need to find out where the load will be taken care. So I have done this front spar, rear spar, that you have to understand what structure you have to use and what cases we would use our wing structure, right? That is why we are calculating the shear flow in the various open sections, right? So we'll do the recall of this problem, and you will understand the case how we solve for the non-idealized structure or channel section or the cut section of open section, C section, right? They given us channel section and we have calculated 3 element. They are giving only vertical load. We don't have the horizontal load. So from this number of solving problems, we identified that when the symmetric about x-axis mean no need to calculate the y bar. Y bar will be 0. Ix will be definitely 0. Then Iyy is not required to solve the problem. Only summation of Ax, summation Ay square, summation Icx is needed. So area is calculated. Area we calculated for each element. 30 into 2 we are getting 30 into 0.2 we are getting the 6 centimeter square for area element 1. Similarly 40 into 0.2 centimeter we are getting the 8 centimeter for the element that is web. For top flange, bottom flange we are getting x, y we calculated from the reference axis, right? And we are getting the Ax square, Ax pi, summation of Icx, and everything we calculated for the elementary table. Then we go for each section, we need to calculate for the Icx, Icy. Icy no need, only Icx. So for section 1 and 2, 3 will be the flange, section 2 will be the web. So Icx is B dq by 12. I told always B will be the horizontal, D will be this direction. So B dq by 12, B dq by 12 for Icx, right? So determination of the centroid x bar y bar we need to calculate. This will not be useful in this problem. So you understand that where will be whether we are getting y bar will be 0 or not. Why? Because we said that when the symmetric about x axis y bar will be 0. So understand that's physics that we are getting this y bar equal to 0, right? So determination of moment of inertia I axis we know the